Hello, my name is Michael Kaler, and I am the lab manager of the GIME Diffraction Facility, which is a user facility housed at the Joint Institute for Advanced Materials at the University of Tennessee, Knoxville. Individuals from UT, outside universities, national labs, and industry are all welcome to use our facilities. In this video, I will show you how to use the Williamson Hall plot feature in HighScore Plus to determine crystallite size in Microstrain. This video is part 2 of a 3-part series highlighting Scherer's equation, Williamson Hall plots, and Rietveld refinement in the determination of crystallite size in Microstrain. All files used in this video are provided by Panalytical and should be located in your computer so that you can practice along with this video or on your own. Before we begin analyzing data using Williamson Hall plots, let's take a closer look at what they actually are. Here we see an example of one, and you will notice that on the y-axis we have plotted B sample times cosine of theta, and the x-axis is sine of theta. We then get a data point for each peak and fit it with a linear trend line. The equation for that trend line is given down below. And if you are familiar with the Scherer equation or have watched our video on Scherer's equation, you might recognize this as a rearranged form of Scherer's equation. We also have the microstrain here. The y-intercept of the linear trend line gives us the crystallite size, and the slope of the line gives us the microstrain. But because this is the broadening of the sample, that means that we need to first determine the broadening caused by the instrument and the broadening observed in the diffraction pattern, because the broadening of the sample is equal to the broadening observed in the diffraction pattern minus the broadening caused by the instrument. So let's first determine the instrumental broadening. In order to do that, we will go to File, Open. If you click Local Disk C, and then go to Program Files x86, Panalytical, HighScore, and Tutorial, you will see a list of files used in the example problems provided in the HighScore help file. For this series of experiments, our samples of interest that we want to analyze are these fluorite samples. I will only work on the raw form, but in order to determine the instrumental broadening, we will use this cerium oxide pattern. So I will double-click, and there we see it. Now, just to make it abundantly clear, you would not use this diffraction pattern in order to analyze your own samples. I am only using this pattern because I am also analyzing data provided by Panalytical. If you want to analyze your own samples, you would need to get some sort of line profile standard, and those are available at NIST. They are cerium oxide, lanthanum hexaboride, and there are others. So once you have your standard, you would collect a diffraction pattern using the same instrument and optics that you use for your samples of interest. Because any time an optic changes, that's going to change your instrumental broadening, and then you would need to collect a new diffraction pattern so that you could calculate the new instrumental broadening. With that out of the way, we will first right-click and search peaks. I will use the settings shown here and just click Search Peaks and Accept. If I zoom in, you will notice that there is a blue curve and red curve. Blue represents the calculated fit and red represents the data. We also see peak markers along the top. Solid markers indicate K-alpha 1 peaks. Dotted markers indicate K-alpha 2 peaks. So I will right-click, zoom out. I will start out by just left-clicking and drawing my zoom box and checking to make sure that all of the peaks have been marked. That all looks good. We do see some peak markers, even though we don't see any peaks associated with them. If we zoom in, we see that the peaks are there, so that's fine. But I will zoom all the way back out. And before I begin any sort of refinement, I will come down here to the additional graphics window, right-click, show graphics, and go to my difference plot, left-click. And this simply shows you the difference between the red curve and the blue curve, so you want these differences to be as small as possible. I will then go to Refinement Control, left-click Global Variables, and come over here to the solver tolerance. I will click here and add another 0 to make it a little bit more demanding. I will hit Enter, and now, while in automatic mode, I will click this button and choose Default Profile Fit. We see that the RWP went down to about 12, and that just gives you a numerical value to judge how well the blue and red curves match, so a smaller value is better. I will come back up here and perform another default profile fit just to make sure that the RWP is stable. It is, it barely changed, so I will leave it at that. And if we zoom in on the peaks, we see that the blue and red curves now match very nicely. Right-click Zoom Out. Even our low-angle peaks match up pretty well. Not perfect, but they're pretty good. I will right-click Zoom Out. Now, I do want to show you one thing that involves the low-intensity region around our peaks. I am going to try to zoom in on these 3 peaks just for an example. And you will notice that even though I draw my zoom box, it's not really zooming in. That's because this button is activated. If we were to click this button, we could then zoom in better. I'll go a little bit more. There we go. Sometimes this region, the low intensity data, will be very close to the x-axis, and zooming doesn't really help for that. If that happens to you, you can right-click, set manual ranges, and then change this minimum intensity to some value such as 0, or you can see here it's -30. Ours looks good, so I will just click OK. But the problem that we see is that here we have the blue curve and red curve, and they match very nicely. But once they get down here, the blue curve suddenly drops down to the green curve much faster than the red curve does. And the green curve is just the background. Now this blue curve drops so quickly because if we go to Global Variables and left-click, we see that the peak base width, which is in multiples of full width half maximum, is set to 20. That means that the width of your peak base is going to be 20 times the full width half maximum of that peak. So if your peak tails are dropping down too quickly, this number is too small. So I will change it to 30, and I will hit Enter in a moment, and you will see those peak tails better fit to the red data curve. So I will hit Enter now, and now you see that the blue curve matches the red curve better. Now once you test your own standard, I don't know if 30 is going to work best for you or some other number, so I will let you judge that. But let's right-click, zoom out, and we will do one more default profile fit. And we see that the RWP dropped a little bit. Now let me just quickly go through. I'm going to make sure that there's no weird fitting going on, that everything looks pretty decent. Sure enough, it all does. So I can right-click and zoom out. Now let's come down here and right-click, Show Graphics, Half Width Plot, and let's look at the full width half maximum statistics. Here we have data points as these open circles, and these represent the full width half maximum of each peak. The curve we see here is a Cagliari curve fit to those data points. The equation for the curve is shown here, and the chi-squared value, which gives you an idea as to how well the data points and curve match each other, is shown here. And once again, a smaller value means a better agreement between the curve and the data points. So at high values of 2 theta, we see that the data points and curve match pretty decently, but at low angles, it looks pretty bad. There is a lot of scatter. One reason for this is that those very tiny peaks that we saw earlier are being used in the determination of this Cagliari curve. and those tiny peaks don't necessarily give us the most accurate profile fits. So let's come up here and go to Tools, Set Peak Status, and here we can set peaks with a relative intensity of less than some user-defined value. I'll just say 1%, and those will be excluded. And what that means is that they will still be profile fit here, but they will no longer be used to determine this Cagliati curve. So I will say OK. We see this curve change, we see the chi-squared value has gotten much smaller, and now we see that these 3 data points are in this bluish gray color. We also see that same color for our data markers here, and if we go to our peak list, we see that color here. So now our data points are matching much better. If we look down here, we still see a little bit of scatter. Part of that reason is because of this tiny little peak here, which I don't think belongs to cerium oxide, but it must be over 1% relative intensity, otherwise it would have been excluded. We can exclude it manually. If you see the red line here, you can right-click, Set Peaks as Excluded, or we can come over here, right-click, Set Peaks Excluded. And now we see that the data point turned that grayish color. And if we zoom out, we see that the data points fit the curve very nicely. Let's now right-click, Show Graphics, Half-Width Plot, and look at the broadening. Our peaks are fit as pseudo-Voigt, and we can tell that by going to Refinement Control, left-click Global Variables, and if you scroll down, you should see this profile function, and it is pseudo-Voigt. We can even pull this to the side a little bit to make it more clear. If you have a pseudo-Voigt profile, you are going to have a Lorentzian component and a Gaussian component. So it plots these separately, and it gives us equations for each curve. It's basically the coefficients that we want to save as our instrumental broadening. To do that, we right-click and take as LP analysis standard. LP stands for line profile. If we do that, we can come back to global variables, scroll all the way down, and we see these Gaussian and Lorentzian coefficients. So now these values here are saved over here. And now we have determined our instrumental broadening. We no longer need this scan, so we can right-click, remove scan, while in scan list. We can go to our peak list. We don't need these peaks anymore, so we can left-click, Control A on the keyboard, and delete. And now, let's go to File, and save this. I will put this in my YouTube folder. And normally I would call this something like parameter file, and then I would list the optics that I used, such as 1/4 divergent slit, 1/2 anti-scatter slit, and so on. And that way, I know that I can use this parameter file with any diffraction patterns that were collected with these optics. If I used different optics, I would have to create a new parameter file. I don't really know what optics were used in order to collect this diffraction pattern, so I will just call this parameter file YouTube. Once that's done, we can then insert a data file. I will go back to HighScore, Tutorial, and I will select this fluorite raw pattern. Now, I highly recommend that the first thing you do after inserting is go back to File, Save As, and some different name. I'll just give it the fluorite raw name that it already has. And you want to do this so that you don't accidentally save over your empty parameter file, because that empty parameter file can be used for multiple sample files in the future. you don't want to have to recreate it every time you want to analyze a sample. So now let's come in here and right-click, determine background. I didn't really do this for the standard file, but it's going to help me a little bit on my data file. Maybe it's not necessary for yours. If we click this button again and look more closely at the background, we see that the background is the green line. If we increase the bending factor, it bends up into the peaks, which we don't want. And if we decrease the granularity, it also bends up into the peaks. Granularity controls the distance between inflection points. So for now, I just want something that's pretty flat and matches the low points in the pattern pretty nicely. So that looks good enough. I'll just accept it. I will then right-click, search peaks again, search peaks, and accept. I will click off of this and once again go through and make sure that all of my peaks have been well marked. There's a little peak there around 58, so that's good. Here we do have something weird. This has two K-alpha-1 peaks, but it should only be one. So I can put my cursor over this right-hand peak marker, and while peak list is open, I can just hit delete on the keyboard. That looks better, so I will continue to scroll to the right. And here I see that the software missed a peak. There should be a peak right here. If I want to add one, I can just right-click, insert peak. Now we see a little peak marker here. I can left-click where it should go. If I want to get rid of that green marker, I can right-click and insert peak again. Now let's right-click, zoom out. Let's come down here and right-click, show graphics, left-click, difference plot. If we go to our refinement control and left-click global variables, we should already have our solver tolerance is good because we set that earlier. So now we are ready to perform another default profile fit. Here we see the RWP is going down to about 8.03. I'm going to try it one more time just to make sure it's stable. It's still decreasing, so I'm just going to keep doing this until it seems pretty stable. There we go. And now let's just take a quick look at the data again and make sure that everything has been fit properly. Here we see a problem. There should be a peak here, but instead the peak is located here. If you go up and click on this button, we will see the individual peak profiles, and sure enough, this should be over here. We can quickly correct that by clicking on this arrow button. And now we see boxes. We see one to the left and to the right of the peak, and then directly in the middle. If we left click and drag on either of the side boxes, it changes the width of the peak. If we left click and drag the top one, we can shift its location. So now that I've put it there, let me right click and zoom out. And I will go back and perform another default profile fit. If we zoom back in on that peak, we see that now it is a much better fit, especially here. So let's right click and zoom out. We'll come down here, right click, show graphics, half width plot, full width half maximum statistics. Our curve is not quite as nice, it doesn't match up with the data points as well as the standard curve did. We wouldn't really expect it to look as good because standards are kind of an ideal sample, but this is still pretty bad. Our chi-squared is about 0.32, which is quite high. Now let's see if maybe getting rid of some of those really low intensity peaks helps that chi-squared. Let's go to Tools, Set Peak Status. Here we still have that 1% that we will exclude, so let's do that. And already this is looking better, and our chi-squared has dropped down to about 0.057. So let's see what the Williamson Hall plot looks like at this point. If you go to your peak list, you should hopefully see the Williamson Hall plot. If you don't, you might be in the wrong desktop. I don't really see the Williamson Hall plot if I am in Rietveld analysis, but I do if I am in line profile analysis. Let me add something real quick that I forgot to include in my original filming of this video. If you are in a different type of desktop, such as Rietveld analysis shown here, or you just don't see a Williamson Hall plot in your peak list tab, then what you can do is go to View and choose Williamson Hall plot. Now you'll notice that we still don't see that Williamson Hall plot, but this little thing did pop up down here. If we left click it and drag up, then we can see the Williamson Hall plot. Now let's continue with the original video. And we see the data points here. Again, the gray ones are ones that we have excluded. And the crystallite size is about 441 angstroms, plus and minus 100 angstroms. And the strain is 0.31%, plus and minus 0.04%. Now this isn't great. An ESD of 100 angstroms when it's predicting 441 angstroms is a pretty large error. So let's see if we can make this a little bit better. Personally, I'm not sure how comfortable I am trusting the profile fit of this peak because we don't really trust the profile fit of this peak. And this one overlaps this one. So I'm going to go ahead and exclude this peak from the calculation. I can just right-click on the data point and exclude. Already that's helped a little bit, and it brought down that ESD to about 80. Let's right-click, zoom out. I notice this orange peak is pretty far off. I can left-click it, and I see the line here, which tells me that it corresponds to this peak. Well, we pretty much again excluded this peak because it's so small and we don't necessarily trust the profile fit we get. These two overlap, so I will just go ahead and also exclude this peak. Right-click and exclude. And now it's looking better. So now it's about 343 angstroms plus and minus 50, and strain is about 0.26 plus and minus 0.03. Maybe we could still go through and find some peaks that we should disregard, but I'm pretty happy with it at this point. The chi-squared is not too terrible, so I will just stick with this fit. There is one more thing I need to show you. If we go to Customize, Document Settings, and choose the Analyze Views Graphics tab, we see this Williamson Hall plot type, and if we click the drop-down menu, we see linear, average, and quadratic. Now what do these three mean? Well, quadratic should be used if you expect microstrain broadening to be the dominant effect on your sample. Linear should be used if you expect crystallite size broadening to be dominant. And average should be used if you think both crystallite size and microstrain are important in your sample. If you work through the 3 high-temperature fluorite samples provided by Panalytical, you will see that the linear Williamson Hall plot does not always work the best. The linear type does work best for the raw pattern, but in the case of the 600-degree pattern, the average plot type seems to result in a better agreement with the Rietveld refinement results from the help file. To be honest, I don't know how to tell you for sure when to switch from one type to the next. One reason I like Rietveld refinements is because they don't seem to make you choose between these different types. Here we see a comparison of results. The first column is the sample name, the second and third columns show you the results provided by Panalytical in the help file, and the last three columns are the results that you will see in this series of videos. If we compare the second and fifth columns, which are outlined in red, we see that the results from the help file fall within the error bars of the Williamson Hall plot results from this video. So that's pretty much it for this video. If you would like to learn more about the Giant Diffraction Facility, please visit our website, and you should see the web address at the top right of your screen. If you have any questions or comments, please leave them in the comment section below. Thank you for watching, and I hope you have a great day.